Tell me what these are congruent to modulo the given number, and make sure your answer is between 0 and the moduli minus 1. So for example, for this first one, give me a number between 0 and 7. For this last one, a number between 0 and 9, and so on. Second question, just about primes and composites. You don't have to prove anything. Just tell me if the number's prime, just say it's prime. If it's composite, give me one factor other than itself and one. You don't have to do all the factors for number two, just give me one factor. For number three, these numbers are each composite. So write them as a product of prime numbers. Show me what the prime numbers are that multiply out to that. Fourth question, there are five pairs of numbers. Use Euclid's algorithm to find the greatest common divisor for each of those. Make sure you show your work for all of these, right? If you just give me an answer for this, I can't give you credit unless I see the steps so that I know that you understand Euclid's algorithm. For five, use the modular exponentiation algorithm that we talked about in class to do this calculation. And again, show me the steps. It'll take, 8 or 9 lines of steps to get there. And then for number six, use Fermat's little theorem to do this calculation. This takes very few lines, probably 4 or 5 lines of work to get the answer, but you got to show me your steps. You got to show me how you got there. You got to um, make clear how you're using Fermat's little theorem to get to this answer and so on. So all of these, as with every problem in this course, you got to show your work, um, but it's not necessarily a lot of work to show. So any questions about those? All right, last call for homework 4. I'm going to close it out in a minute. All right, so let's run through the questions on homework 4 because these are fair game for the midterm. So the stuff that we started on Monday, mathematical induction, that is not on the midterm. The midterm goes up through and including the number theory stuff. Um, and so definitely everything we've done on propositions up to here, including this homework set. So let me just run through a few of these proofs because I started eyeballing the submissions and it looks like people have the right idea, but there are some technicalities that you want to be careful of. So let's just start with number two. Um, Number two says prove that if n is even, then 6n plus 4 is even. All right, so what's our proof look like? Number your statements. Most people are doing that. That's good. Let's start with the hypothesis. N is even. That's a hypothesis. Um, you're not required to do a direct and an indirect proof if it doesn't say do both. You just have to do one. And for a lot of these, one of them is possible. The other one is pretty difficult to do. For this one, a direct proof works well. Really hard to do this with an indirect proof. Um, so if you're trying to do one of these proofs and it's just not clicking, try doing it the different way, directly or indirectly. This one, a direct proof will work. So proposition one, n is even, that's the hypothesis. Proposition two, let's just say there exists an integer k such that n equals 2k. And that's the definition of even and proposition one. So we have never described a law of even multiplication or even addition or odd multiplication or things like that. So you don't want to just say, well, 6 is even and n is even, so 6 times n is even. That's not a law of logic. That's something that you could prove. That's basically what you're trying to prove here. That's what we proved when we said, for example, if n is even, n squared is even. But we went through a series of steps, several steps, to prove that. It's not a law of logic that we're given, right? We're given closure of integers, we're given basic arithmetic operations, and that's about it. Everything else is, those laws of logic. Um, so we know n can be written as 2k, where k is an integer, but we got to do something with that. And what most people figured out to do is to plug that version of n into 6n plus 4. So you can write something like 6n plus 4 equals 6 times 2k plus 4. And that's just substitution of equation 2, right? N equals 2k into this expression. So at this point, some people wrote down something like 12k plus 4. And at that point, you lose credit. What's wrong with this statement 4? There's one big problem with it.
It's not a declarative statement.
It's not a declarative statement, exactly. It's not a proposition. Now, you can make it a proposition pretty easily by saying something like 6n plus 4 equals. Or I've said in this course, you can um, skip the complexity of that and just continue proposition 3 and say this equals 12k plus 4, which equals 2 times 6k plus 2, and that's all algebra. And that's totally legal, right? If you wanted to be strictly formal, you could write 6n plus 4 equals 6n plus 4 equals and have each of those be a separate proposition. But we can take this to be one big long proposition. 6n plus 4 equals that, which equals that, which equals that. And once you've got this in whatever form, now we've written 6n plus 4 equals 2 times this thing. Go ahead and state that this thing is an integer. And that's from closure of int and the fact that k is an integer, which was part of proposition 2. And then tie that all together. 6n plus 4 equals 2 times something, which is stated to be an integer. That means 6n plus 4 is even. And that follows from proposition 3, proposition 4, and the definition of even. And that's what you wanted to prove. 6n plus 4 is even. So that's a full credit proof. All right. Questions on that? So let's do one of the indirect ones. So question 4, for example, very hard to do that with a direct proof. But we can make an indirect proof out of that. And it's similar to when we showed that if n squared was even, n was even. Well, that's exactly what we're trying to show. Um, so let's just do that again. Prove if n squared is even, then n is even. Okay, so this is an indirect proof. Indirect proofs write a little differently. Um, Step one, negate the conclusion. We're trying to show n is even. So my first statement is going to be n is odd. And that's going to be the negation of the conclusion. Since everything else is coming after this, when I reach a contradiction, I can say this cannot be true, right? Because just by assuming that this was true, I found a contradiction. So this has got to be false. That's going to tell me since n is not odd, n's got to be even. So we start off with n equals odd, and now we want to say something about n squared. Well, I can say n equals 2k plus 1, where k is an integer. I would write that differently. I say there exists an integer k and z such that n equals 2k plus 1. But if I see this, I'll be okay with that. That's the definition of odd. And then do your substitution. N squared equals 2k plus 1 squared equals 4k squared plus 4k plus 1. Factor out your 2. That's all algebra. And substitution of n equals 2k plus 1. Substitution from proposition 2. And then make sure this is twice an integer plus 1. Just go ahead and state 2k squared plus 2k is an integer. That's closure of ints. And don't forget the important fact that k is an integer, which comes from proposition 2. And now you can tie it all together. N squared equals 2 times this plus 1, and this is an integer. That means n squared is odd. And that's propositions 3, 4, and definition of odd. But at this point, we still need to bring in our hypothesis. N squared is even. That's the hypothesis, and that's a contradiction. Therefore, this first statement must be false and is even, therefore, and that's what we wanted to prove. All right, and then let me just run through number 6. 6 said prove that if a divides x and a divides y, a divides 5x minus 3y. And this is fundamentally no different from these other proofs, but it's a different problem domain. It's looking at divisibility. But the way we're going to approach this, exactly the same thing. So prove if a divides x and a divides y, then a divides 5x minus 3y. And this looked pretty good. The ones that I spot checked. Looks like most of you were on track with this. Again, it's the details sometimes that can cause some issues. But a direct proof will work here. So let's start with our hypotheses. A divides x, that's a hypothesis. A divides y, that's a hypothesis. And make sure this is a vertical line. And then use the definitions. And everyone I saw using this, they use different integer constant values in here, which is great. That's another potential trip point. So the definition of a divides x is there exists an integer, let me call it k, such that x equals ak. That's the definition of divides and proposition one. And then four, and this is what most people did great, they pick a different integer, right? So let's say there exists an integer j such that y equals a times j. That's the definition of divisibility and proposition two. And then, as we tend to do with these things, substitute, right? So we want to show 5x minus 3y is a multiple of a. So let's try to write this in some form that involves a's. Well, it's kind of crying out to us because we've written x in a way that involves a's. And so if we plug that in for x, there's going to be an a in here, and the same with y. So let's just do that substitution. 5x minus 3y equals 5 times ak minus 3 times aj. And lo and behold, we can factor an a out of that. So it's a times 5k minus 3j. And that's algebra and propositions 3 and 4 that we used for substitution. And then one more thing to do. We've shown 5x minus 3y equals a times this thing. We've got to know that this thing is an integer. Otherwise, we don't have divisibility. And we can just state 5k minus 3j is an integer. And the reason is closure of ints and the fact that k is an integer and the fact that j is an integer. And then we're done. 5x minus 3y equals a times an integer. That means a divides 5x minus 3y. And that's the definition of divides along with proposition 5 and proposition 6. That's what we're trying to show. So that's the end of our proof. All right. So questions on any of that? All right. Um, so I posted a short synopsis of some of the topics we've been doing under a list of possible midterm topics. Um, there should not be any surprises in here. This is just kind of going through what we've been doing and trying to list them in categories. But basically, set theory, which was where we started, which included functions, summations, very, very, very brief mention of matrices. Um, and then mostly propositional logic has been the bulk of our time. And that boils down largely to doing proofs, but also things like fallacies, making sure you understand what fallacies are, quantifiers, which is like for all and there exists. Um, the notion of logical equivalence and how that relates to identities, and so on and so forth. Direct and indirect proofs. You can expect to possibly see proofs involving even or odd numbers, um, or proofs involving things like, question 4 from section 3.5, the previous week's homework. Number theory, the idea of divisibility, like that last problem we just did, basic notions about prime numbers, being able to find the GCD of two numbers. I'm not going to ask you to do modular exponentiation or Fermat's level theorem yet because that's on this week's homework. But we did some GCD problems in class, so that's fair game. So any questions about that or Um, Anything else related to the midterm? So again, your midterm is Monday, 12 o'clock, and it's room 155 in the STEM building. And please bring a photo ID. All right, questions on what we were doing with induction. We just started that on Monday, and we're going to go through a lot of examples of induction today. But any questions to start with? All right, let's just keep going through some examples. So we did a first example where we were looking at sums of consecutive integers, and that one got kind of algebraic. Let me do another one like that, and then we'll switch gears a little bit. So here's a theorem. Well, let me do it like this. Basically, the sum of the first n odd numbers gives you n squared. So 1 plus 3 plus 5 is 3 squared. That's 9. 1 plus 3 plus 5 plus 7 is 16. That's 4 squared. So the sum of the first n odd numbers is n squared. So if I wanted to write this using summation, sum from I equals 1 to n of 2i minus 1 equals n squared. If I want to think of it as dot dot dots, this would be 1 plus 3 plus sum all the way up to and including 2n minus 1 is n squared. So let's prove this with mathematical induction. And so to do a proof by induction, we need to have a family of propositions. So I'm going to say let P of n be the proposition 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 equals n squared. Please take the time to actually write that out. Don't say let P of n be sum equals n squared. Write it out. It'll help you. All right. So we want to prove P of n for all n bigger than or equal to 1. All right. So prove. First, we got to do the base case. Since we're trying to prove P of n for n bigger than or equal to 1, we want to prove a base case of P of 1. So P of 1 is the proposition. Well, it looks like we want to add from 1 up to 2 times 1 minus 1. That's just 1. So P of 1 is really just the proposition that 1 equals 1 squared. And we're allowed to just look at that and say, yeah, that's true. So establishing the base case doesn't take much work. All right, go to a new sheet here. The inductive step, we want to prove P of n implies P of n plus 1. Right? Which again is different from proving that P of n itself is always true. We're just showing if P is true for n, it's true for n plus 1. So let's do that. So step one, I'm going to assume the hypothesis P of n. Step two, I'm going to write out what P of n is, which is right here, 1 plus 3 plus 5 plus 2n minus 1 equals n squared. That's the definition of our proposition P of n. All right, at this point, I may be stuck. I want to show P of n plus 1. I probably have no idea how to get there from here. So I'm going to draw a little squiggly line over here, and I'm going to say ignore. And if you do that, I will ignore everything over here. Won't count it as part of your proof. This is an area where I'm going to kind of think out loud. I'm going to look at what I want to get to and play around with it in approximate ways that may not be part of a valid proof, but I'm just going to explore. And if it's in this ignore section, I can do that without consequence. So I want to show P of n plus 1. That's what I want to get to at the bottom here. If I get P of n plus 1, I'm done. So in order to know how to get there, it helps me to look at what P of n plus 1 says. So P of n plus 1 says 1 plus 3 plus 5 plus 2n minus 1 plus the next odd number, 2n plus 1, equals n plus 1 squared. All right, really, really important point here. If I take that equation and I put it over here, my proof just went invalid. Right? I don't have any basis for saying this is true. So if I write this over here, the proof falls apart. The reason I'm doing a line and the word ignore is so that I can write this and not have it be considered part of the proof. But I want to write this down. It's the goal I'm after, right? And I want to figure out how can I get from here to here? Because what I want to do is write this down somewhere over here and say, therefore, P of n plus 1, and then I'm done. But I'm not allowed to just write it down just because that's what I want to see. I've got to have a reason for it. So if I write that down right here, there's no reason, the proof is invalid. So I put it over here in this sort of thinking out loud area. And now I ask myself, I know this. What can I do to get to this? So any ideas what I can do to what I've got that might move me towards what I'm after? And I would look at this part and notice that that is the same as this. So this whole left side that I want to work with is really just this with one more thing added to it. And most likely I need to use this somehow to show this. Right? I'm proving P of n plus 1 given P of n. So I want to use this somehow. I don't really have an n squared anywhere, but I do have a big chunk of my left side right here. So that gives me an idea. Let's just add 2n plus 1 to the left side. And if I do that, my left side's going to look exactly like this. But if I add something to the left side, I have to add it to the right side also. And as long as I'm adding the same thing to both sides of an equality, I don't have to explain it. I don't have to say why I added 2n plus 1. I can just say, that's algebra and proposition 2. And at this point, it may not even be clear why we did that. The only thing we know is that suddenly we've written a proposition whose left side is the same as the left side of the proposition we want. And so the question is, can we do anything with the right side to make the right side look like the right side that we want? And in fact, we can, because n squared plus 2n plus 1 is just n plus 1 squared. And that's just factoring n squared plus 2n plus 1. And so now I can reflect on this proposition that this sum is equal to n plus 1 squared. And if I look at my original definition of P of n, this is exactly P of n plus 1. And that follows from proposition 3. Therefore, P of n implies P of n plus 1. And that, taken together with our base case, tells us P of n is true for all n bigger than or equal to 1. And that's mathematical induction. And that's what we were trying to show. So that's the end of our proof. All right. Questions yet? So there's a fact we bump into in computer science fairly often, which is this. If you add up the powers of 2 from 0 to n, you get 2 to the n plus 1 minus 1. For example, for n equals 3, 2 to the 0 plus 2 to the first plus 2 squared plus 2 cubed is 1 plus 2 plus 4 plus 8, which is 15, which is 2 to the fourth minus 1. And this comes up a lot. If you think about what this is saying, if we're adding up all the powers of 2 from 2 to the 0 on up to n, if we were to write this number in binary, it's just a bunch of ones. Because a bunch of consecutive 1 means my number is 2 to the 0 plus 2 to the 1 plus 2 to the 2 and so on. And in binary, a number of this form is always 1 less than a power of 2. So if I write this, that's the number 255. It's 1 less than 256. If I do that 32 times, That's a number which is the largest integer we can write as a signed 32-bit number, and it's around 2 billion. If you're setting up networking on a computer, or if you're looking around at crash dumps or something like that, you often see numbers like this pop up, right? Well, an F in hex is just 4 ones in binary. So this is a representation of 32 ones in binary, which is the sum of the first 32 powers of 0, which is 2 to the 32 minus 1, which is the largest number you can represent. It's also a minus 1. All right, so this pops up a lot. Um, and we can prove this, and we can prove it using mathematical induction. So let's say let P of n be the proposition. And I'll do this with dot, 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 dot. So the sum of the powers of 2 from 0 to n is 2 times 2 to the n plus 1 minus 1. So let's prove P of n for all n bigger than or equal to 0. So what is our base case here? P of 0 this time, right? Because we want to show it for n bigger than or equal to 0. So our base case is P of 0. Awesome. So what does P of 0 say? What does that proposition actually say? And this is easier on a microphone than typing, I suspect.
2 to the 0 is 2 to the 1 minus 1.
Perfect. Thank you. Basically, sum from 0 to 0, that's just 2 to the 0 equals 2 to the 0 plus 1 minus 1. Well, 2 to the 0 is just 1. 2 to the 1 minus 1 is 2 minus 1. That's 1. 1 is equal to 1. So this is true. So we've got our base case. So now we have to prove the inductive step. So prove P of n implies P of n plus 1. It's boilerplate at this stuff. We're always going to do kind of the same things in the beginning of these. I'm going to start with P of n. That's a hypothesis. I'm going to write what P of n says, which is the sum from I equals 0 to n of 2 to the I equals 2 to the n plus 1 minus 1. That's the definition of P of n. And then again, I need to figure out where to go from there. So I want to show P of n plus 1, which says what? Well, it says the sum from I equals 0 to, instead of n plus 1 of 2 to the I equals 2 to the, well, instead of n plus 1, it's going to be n plus 1 plus 1, 2 to the n plus 2 minus 1. That's what I'm after. And just like before, I've got a proposition which captures most of this left side. I just have to add one more thing to this. So let me carefully write the following. Sum from I equals 0 to n plus 1 of 2 to the I equals the sum from I equals 0 to n of 2 to the I plus 2 to the n plus 1. Everyone agree with that? That's just properties of summation. We did those week 2. We can take the sum, we can break it into the sum of everything up to n, and then just add the n plus first term. But now I can use proposition 2, and I can substitute. The sum from 0 to n is actually 2 to the n plus 1 minus 1. So this thing becomes 2 to the n plus 1 minus 1 plus 2 to the n plus 1. So I'm just substituting from proposition 2. And then how do I simplify this expression? Using a little bit of algebra. What if I rearrange the terms? How can I simplify it now?
Um, are you going to be 2 into 2 to the power n? Um, is that
Yeah, that sounded close. Can you say that again?
it's going to be 2 into 2 to the power n minus 1. Something?
Yeah, so 2 to the n plus 1 plus 2 to the n plus 1, that's 2 times 2 to the n plus 1 minus 1. A plus A is equal to 2A. So this is twice 2 to the n plus 1 minus 1. And then this says multiply 2 by itself n plus 1 times. And this says multiply by 2 once more. This is just 2 to the n plus 2. And we keep that minus 1 there. So that's more algebra. But now what have we written? We've written that the sum of from 0 to n plus 1 is equal to 2 to the n plus 2 minus 1. That is what P of n plus 1 says, right? If we take the sum up to n plus 1, we get 2 to the n plus 2 minus 1. So we've just shown P of n plus 1. Therefore, P of n implies P of n plus 1. And that together with the base case tells us P of n is true for all n bigger than or equal to 0. That's mathematical induction. And that's what we wanted to show. All right, let's shift gears. Let's get away from the algebra for a minute. You know De Morgan's theorem, right? So De Morgan's theorem, it works on propositional logic, it works on Boolean equations, it works on sets. Let's just pick a version of this from 250, which is AB bar equals A bar or B bar. So just good old logic. The NAND is equal to the OR of the complements. So suppose we know that this is true. We're given this, Izad told us, or I told you, or someone told you, and we know that this is true. So there's a version of this for three variables. Right? This is also true. But suppose we want to prove this. And forget about induction for a minute. Let's just go back to engineering CSE 250 and just think about Boolean operations. And suppose we're told, okay, you can use this. This is given, this is a fact. How can we prove this? And it turns out it doesn't take too much work if we look at this the right way. Because remember, these statements like this does not just apply to A and B. It also applies to X and Y. It also applies to R and T. It also applies if A is some sort of expression. A might be P and Q. And we could say P and Q and B bar is equal to P and Q bar or B bar. And that would be correct. So this is where I suggest using boxes instead of letters. Right? So square triangle bar equals square bar or a triangle bar. And I can put anything in here that I want, as long as what I put in this box is in that box and that triangle is in that triangle. So let me write this a little bigger so I can actually write in here. And let me put into my box AB. And let me put into my triangle C. So this is just using plain old De Morgan's theorem on two variables. Except my first variable is this, compound thing, A and B. My second variable is just C. So what De Morgan's theorem on two variables is telling me is this. Right? That's what I get directly from De Morgan's theorem. But now I can use De Morgan's theorem a second time, and I can replace AB bar with A bar or B bar. And I'm going to leave my C bar as is. And what pops out of this thing I'm trying to show? ABC bar equals A bar or B bar or C bar. So I've got this new version of De Morgan's theorem for three variables. But suppose someone says prove this. Prove that it's true for four variables. Can we do this? Yes, absolutely. And I'm going to do it exactly the same way we just did it for three variables. I'm going to write De Morgan's theorem like this. And in my box, I'm going to put A, B, C. And in my triangle, I'm going to put D. And so the left side of this equation is just A, B, C, D bar. And the right side is ABC bar or D bar. And remember, we proved this three-variable version of De Morgan's theorem, so I'm going to take that and I'm going to replace ABC bar with A bar or B bar or C bar. And I'm going to keep my D bar. And just like that, we've proven the four-variable version of De Morgan's theorem. All right. Could I do this one more time and prove this is true for five variables? Does everybody think that's possible? Cool. If we had enough time, could I do this 5 million times and prove De Morgan's theorem for 5 million variables? Is there anything that would stop me other than time and patience and ink and paper and dying of old age? Right? I could definitely do it, but I don't want to. But I'd still like to know De Morgan's theorem works on 5 million variables. So this is what mathematical induction will do for us. It will let us take our idea on how to go to 5 variables, 6 variables, 10 variables, and it'll let us formalize it. So yeah, knowing induction stops me. All right. So let's do a 5-minute break. We come back, we'll formalize a proof of De Morgan's theorem for n variables and see how that works. And then we'll go from there. So let's come back at 1 o'clock. All right, I'll see you in 5 minutes.
You're muted.
Thank you. So let's prove De Morgan's theorem for n variables. So P of n is the proposition that anding n variables is like, and taking the negation is like taking the OR of n negated variables. And let's prove P of n for n bigger than or equal to 2. It's also true for 1, but it's kind of a silly theorem for 1. It says A1 bar equals A1 bar. So let's prove it for n bigger than or equal to 2. So our base case we need to prove this. And this is true because this is De Morgan's theorem. And we know De Morgan's theorem is true. So our inductive step, prove P of n implies P of n plus 1. All right, step 1, P of n, that's our hypothesis. Step 2, let's just write out what this says. And that's just the definition of P of n. Well, what have we been doing? We've been breaking up all the things we want to NAND together into one fewer set of things and then one extra variable. So let's just do that. So this NAND of n plus 1 things is equal to the following. Right? This is just associativity. But let me add some extra parentheses here so we can see this as two things being NANDed. And De Morgan's theorem tells me that this is equal to the NOR of the first thing ORed with the NOR of the second thing. And that's just De Morgan's theorem on two variables, which we certainly know because that's actually our base case. But we know P of n, we know that this is equal to that. And so we can rewrite this as the following: A1 bar or A2 bar up to AN bar plus AN plus 1 bar. And that's proposition 2. And this is what P of n plus 1 says. It says the NAND of n plus 1 variables is the OR of those n plus 1 variables complemented. So this proposition 3 is the statement of P of n plus 1. And that's just the definition. Let me put a line here. That's the definition of P of n plus 1 in proposition 3. So therefore, P of n implies P of n plus 1, and therefore P of n for all n bigger than or equal to 2. And that's what we wanted to show. All right, is this making any sense? Got a thumbs up, 2 thumbs ups. Okay, cool. Thank you. So these are all examples of mathematical induction. It's a general principle, but we can apply it to a lot of different problem areas. And part of the trick is going to be to recognize places where we can apply this. And we kind of intuitively understand the principle. It's what we sometimes just call et cetera, right? Um, just keep doing this until you get there, right? When we have that kind of understanding of something, it's like we know the series of steps to follow. We don't necessarily want to follow them, but we believe that if we did, we would get somewhere, right? I don't want to put one foot in front of the other a million times, but if I did, I would get to the end of my journey of a million steps, right? Um, I have no doubt that I could do that. I just don't feel like it. Well, exactly the same thing here. We could prove De Morgan's theorem for 10 million variables. Don't want to, right? So induction is our shortcut. It lets us say, okay, well, it works for any number n, whether that's 2 or 5 or 10 million. All right, let me go back to a mathematically complex one. So a comment on these algebraically intense proofs that we're doing, right? This is not an algebra course. You've passed Math 111, you don't have to go back to that, right? So if you don't know how to do the algebra or you can't get things to work out right algebraically for these proofs, I'm not all that worried about it. When I ask you to do questions involving mathematical induction, what I want to see is clear thought process involving mathematical induction. And if you can get your problem down to some point and you know where you want to go from there, but you can't figure out how to get there, stop there and say, I'm trying to turn it into such and such, but I don't know how. And then show me what you wanted to turn it into and how you would finish the proof from there. If you do that within reason, you can still get close to full credit. Now, if you write the original thing you're trying to prove and say, I can't figure out how to get here, and then you say QED, you don't get a whole lot of credit. But if there's one step in the middle that's sort of eluding you, or if you're getting tangled up in the math, don't sweat it, right? Don't spend hours working on a problem that's hamstringing you with the algebra, right? Because it's not an algebra course. Algebra is important, but that's not the focus of this course. That's not where I want you spending all of your brain cycles. So this is an example of using induction to prove something that gets pretty heavy algebraically. I'm going to go through it anyway, but don't take it as a sign of, oh, this is what my next week is going to be, is this kind of stuff. No. Um, Focus on the idea of induction. The algebra is just supposed to be a tool that lets us do the legwork. If we can't do that, that's okay. You can still learn induction. So here's an interesting thing we can prove. Let's prove that 3 divides n cubed minus n, where n is bigger than or equal to 0. So n cubed minus n is always a multiple of 3. Well, is that true? I don't know. Never really thought about it. 5 cubed is 125. Minus 5 is 120. That's a multiple of 3. 3 times 40. 4 cubed is 64. Minus 4 is 60. That's a multiple of 3. 2 cubed is 8. Minus 2 is 6. That's a multiple of 3. 1 cubed minus 1 is 0. That's a multiple of 3. 0 cubed minus 0 is 0. That's a multiple of 3. So, I mean, it feels plausible. 10 cubed is 1,000. Minus 10 is 990. That's a multiple of 3. So let's try to prove this with mathematical induction. So let P of n be the prop. 3 divides n cubed minus n. All right, P of 0 is the proposition that 3 divides 0 cubed minus 0. Does 3 divide 0? Yes, absolutely. How do we know? Because there's an integer, k, such that 0 equals 3 times k. In particular, k equals 0. Right? There's something I can multiply 3 by to get 0. I can multiply 3 by 0. So 3 divides 0. Every integer other than 0 divides 0. So P of 0 says 3 divides 0. This is true. So now we just have to prove our inductive step. Prove P of n implies P of n plus 1. All right, step 1, P of n. That's the hypothesis. Step 2, 3 divides n cubed minus n. That's the definition of P of n. All right. There's nothing clear to do here. There's nothing clear to substitute or combine or simplify or anything like that. This is definitely going to benefit from doing some thinking on paper. So here's an ignore section. And I want to show P of n plus 1. I want to show 3 divides n plus 1 cubed minus n plus 1. And all I've got is this. 3 divides n cubed minus n. Which may not look like it has a lot to do with n plus 1 cubed minus n plus 1, but let's expand this out. So if you do FOIL 3 times, n plus 1 cubed is n cubed plus 3n squared plus 3n plus 1. And then I want to subtract n plus 1. So that's going to give me n cubed plus 3n squared. 2n minus n will be will be 2n, and then plus 1 minus 1 will cancel each other out. So this thing is equal to n cubed plus 3n squared plus 2n. Well, we're getting closer. We've got an n cubed here and here. We've got an extra n squared here, and we've got a 2n, and we want a minus n. So this is a trick. sometimes you can make an expression more complex, and that ends up letting you make it simpler. That's a life lesson, by the way. Sometimes we can make an expression temporarily more complex, and that will let us ultimately simplify it. So I combined everything I could up here, but if I look at this again, notice I had a minus n right there. Now I combined the 3n and the minus n to get 2n, but if I hadn't done that, I could have left it in that form, and now there's my n cubed minus n. And I know n cubed minus n is divisible by 3, so this circled stuff is divisible by 3. Well, take a look at what else I've got. I've got a 3n squared. Is that divisible by 3? Absolutely. It's 3 times n squared. And I've got a 3n here. That's divisible by 3 too. So these two terms are divisible by 3 because there's 3 sitting right in front of each of them. And this circled stuff is divisible by 3 because that's our inductive hypothesis. So there's a solution in here. Right? Now this is not something I can just plop over here, right? For one thing, I wrote this statement down and I have no basis for that, so that would make the whole proof fall apart. But the goal is to kind of like work backwards. I can see why this whole thing is divisible by 3. If I can work that back into n plus 1 cubed minus n plus 1, then I can say p of n plus 1. So this is where we get into a little bit of heavy lifting. So I'm going to do n plus 1 cubed minus n plus 1 equals n cubed plus 3n squared plus 3n plus 1 minus n minus 1. That's algebra equals n cubed minus n plus 3n squared plus 3n. The plus 1 and minus 1 cancel, equals n cubed minus n plus 3 times n squared plus 3n. That's all algebra. Yeah, that's just algebra. All right. So the intuition I had was this thing's divisible by 3 because, proposition 2, this thing's divisible by 3 because it's 3 times an integer. So let's just formalize that. So I'm going to say n cubed minus n equals k times 3. I'm going to say there exists an integer k such that n cubed minus n equals k times 3. And that's just proposition 2 and definition of divides. And so now I can say n plus 1 cubed minus n plus 1 equals, I'm going to replace n cubed minus n with 3k. And I'm going to leave the 3 times n squared plus 3n, which is equal to 3 times, and now I'm going to factor out that 3. So this is 3 times k plus n squared plus 3n. And that's just proposition 4 and algebra and proposition 3. And then just to be precise, we want to note that this thing is an integer. So k plus n squared plus 3n is an integer. And that's properties of integers or closure of integers. and the fact that k is an integer. And so what have we shown? N plus 1 cubed minus n plus 1 is 3 times an integer. That means 3 divides n plus 1 cubed minus n plus 1. And that comes from 5, 6, and the definition of divisibility. And that's p of n plus 1. And now we're just doing the wrap up. We can say, therefore, p of n implies p of n plus 1. Therefore, p of n for all n bigger than or equal to 0. And the reason is mathematical induction. And that's the end of the proof. So the same basic process, right? Figure out what you're trying to prove, define a family of propositions so that you can state your proof in terms of that family P of n. If you don't tell me what P of n is, you don't have a proof. So you got to define what that family of propositions is, state what you're trying to prove in terms of that, prove your inductive step, which is usually just demonstrating that it's true, and then start with the hypothesis, write out what it means, and then do something to try to get to P of n plus 1. Sometimes it's 1 or 2 steps, sometimes it's a lot of steps. And then once you've got P of n plus 1, that proves the inductive step. And together with the base case and mathematical induction, that proves P of n for all of your n. All right, are you ready for the most important example you're going to see this entire course? This is the gold nugget that is CSE 215. And it's probably not going to take 25 minutes, but it's going to take a lot of the rest of the time. But this is the goods. This is a bizarre example, but I'm going to tie it into what we're doing in CSE 222 today and tomorrow. What we already did today, what we're doing tomorrow, and what we're going to do the rest of the course. So let me do a different sort of problem here. So let's suppose that you have a kitchen floor, and your kitchen floor is covered with all these little tiny tiles. They're like, an inch by an inch or something. And there's, grout, this material you put in between the tiles. It's white and makes the whole thing look nice and fancy. Um, and if you ever had a floor like this, they get dirty over time. And that grouting material in between the tiles gets really hard to clean. And if it's in the kitchen, it can start getting downright nasty. So after a while, people like to retile their kitchen floors. So you want to rip up all of this and you want to go get a box of new tiles and lay them all down nicely spaced and get some fresh grout and fill it in between and let it sit for a day or two, and you've got a new kitchen floor. All right, so that's what we're going to do here for the next few minutes. We're going to talk about tiling a kitchen floor. And there's no real algorithm you need for doing this. If you've got a 10 by 10 floor, you get a box of 100 tiles, and you lay them down, you try to space them evenly, you fill them, and so on and so forth. Um, so here's the setup for this problem that makes it more interesting. Suppose you don't have a bunch of tiles. Suppose you went to some discount store and they had really good prices on tiles, and so you ordered a huge box of these, and you get home and you open them up and you discover the tiles are not little 1 inch by 1 inch squares. The tiles are these funny L-shaped pieces that look like this. They're three tiles stuck together. And you're not allowed to cut them. If you try to cut tiles without the right kind of saw, they just shatter. And so you're wondering, can I cover my floor using these funny L-shaped pieces of tile? Now, in some cases, sure, if your floor happened to look like this, where it was like 3 by 2, a really tiny room, yeah, you could use two of these L-shaped tiles and cover it, no problem. And if it was 30 by 20, you could just repeat this 10 times across and then repeat that 10 times up. You could still tile your floor. But if your floor was shaped like this, there's no way you can use these to tile it. Sorry, there is. If it was shaped like this, you can't tile it. And you can't tile it for one thing just by counting tiles. I've got 1, 2, 3, 4, 5, 6, 7, 8 squares to fill, and every time I put down one of these, I cover 3 squares. Well, if I put down two of these, I can cover 6 squares. If I put down three, I'm going to have to cover 9 squares. There's no arrangement of these that will cover 8 squares. Now, if I can cut it, no problem. I can definitely tile. If I'm allowed overlaps, I can tile any size floor that I want, but then you've got a tile sticking up out of the ground, and that's no good. So we want to study this question, when can we tile a floor using these L-shaped pieces? And there's a theorem, we can call it the great floor tiling theorem, which says that if our room has dimensions where each side is the same power of 2, so it's a 2 to the n by 2 to the n room, and if anywhere in that room there's exactly one tile we do not want to cover, then yes, we can cover the floor with these L-shaped pieces. That's the theorem. So we're going to prove that, and we're going to prove it using mathematical induction, and then we're going to do something interesting with that proof. All right, so is everybody clear on the setup? We've got a 2 to the n by 2 to the n floor. Somewhere in there, there's one square that we don't want to cover. We're going to prove we can cover all the remaining squares using these L-shaped sets of 3 tiles. All right, gonna need more paper. So let's start off with a family of propositions. Let P of n be the proposition you can cover a 2 to the n by 2 to the n room with one missing spot. by using these L-shaped tiles. There's a lot of detail in there I've said, but I haven't written. You're not allowed to overlap. You're not allowed to cut the pieces, and you have to cover every square in that room except for the one missing spot. So that's what P of n says. It says there's a way to do that. And we want to prove P of n for all n bigger than or equal to 1. So for a 2x2 room, a 4x4, an 8x8, 16x16, and so on. Okay, and we're going to do this using mathematical induction. So the first thing we need is a base case. And let me put this over here. So the base case is to prove P of 1. Okay, what does P of 1 say? It says if I have a 2x2 room with one missing spot, I can cover it using these L-shaped pieces. Is that true? 2x2 room with one missing spot. Can I cover it with these L-shaped pieces? Yes, absolutely. And I can prove it pretty easily by just showing how I would do this. So here's a bunch of 2x2 rooms. I'm supposed to have one missing spot. There's only 4 possibilities. It might be that one that's missing, or this one, or this one, or that one. Well, if this square is missing, I can take my L-shaped piece and put it down like that, and I'm done. If this one's missing, I can tile it like that. If this one's missing, I can tile it like that. And if the lower left corner is missing, I can tile it like that. So that's kind of an exhaustive proof that actually P of 1 is true. All right, so now P of 1 is true. So now let's prove the inductive step. P of n implies P of n plus 1. And I'm going to do some hand waving. I'm not going to make this, a purely mathematical proof. I want to convince you it's true rather than, get good grades from my math teacher. So we're going to kind of wave our hands at this, but we're not going to do any funny business. So let's suppose P of n is true. All right, that's our inductive hypothesis. So picture a room that's 2 to the n plus 1 by 2 to the n plus 1. If we can show that this can be tiled with the n-shaped pieces, then we'll have shown that P of n plus 1 is true, and then we can use mathematical induction and claim P of n is always true. So I need to tile this bigger room. Oh, and there's a missing square somewhere, remember. So, I don't know. I'll just randomly pick a square right here that's going to be missing. All right, here's what I'm going to do. I'm going to break this room into 4 sections. So if I do that, this is going to be half of 2 to the n plus 1. This is going to be 2 to the n. And this is going to be 2 to the n. And this will be 2 to the n. And this will be 2 to the n. Everything is 2 to the n. In other words, each of these quadrants is a 2 to the n by 2 to the n room. And I claim I can tile this upper left quadrant using L-shaped pieces. And how do I know that I can do that? How do I know I can tile this upper left quadrant? Yeah, because P of n is true, and P of n says if I have a 2 to the n by 2 to the n room with one missing square, I can tile it. So I got that quadrant covered. And that's because of P of n. Now, does P of n apply to these other quadrants? No, right? P of n only works if I have one missing spot. And I don't have any missing spots in here. So let me temporarily take out a spot. I'm just going to take out this corner right here. And now this is a 2 to the n by 2 to the n room with one missing spot. I can tile the rest of this because of P of n. And I'm going to take out a corner right here. And P of n tells me I can tile the rest of this. And I'm going to take out a corner right here. And P of n tells me I can tile the rest of this. So I've tiled my entire room except for these three pieces that I removed. Well, those three pieces, they're in the exact shape of one of our L-shaped tiles. So I pop one more tile down here, and I've done the entire room. Right? Therefore, P of n plus 1. Therefore, P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 1. And we're done. So that's a different sort of proof, right? But it's a totally valid proof, right? It's using the inductive hypothesis P of n 4 times, first to cover this quadrant that already has a missing piece. And then in order to use it on this lower left quadrant, we temporarily ignore one spot. And P of n tells us we can tile the rest and do the same thing here and here. And then we've got the whole floor tiled except that missing spot and these three spots, but that set of three spots gets filled in with one tile. So this proof tells us that, yeah, nice observation. This proof tells us that we can do a 2 to the n by 2 to the n for any value of n bigger than or equal to 1, but it doesn't tell us how to do that. It just guarantees that if we can do a 2 to the n by 2 to the n, we can also do a 2 to the n plus 1 by 2 to the n plus 1. But let's see how we would actually do this. So suppose I have a room that's 16 by 16. And I've got this big box of L-shaped tiles that I got cheap. And I already tiled my floor, but I've got, 10,000 tiles left over. So I decided to open a little side business where I tile people's kitchen floors for them. As long as their kitchen is 2 to the n by 2 to the n, and there's like a water pipe somewhere, one square they don't want covered. So it's a peculiar business model. So I will tile your 16 by 16 floor for you with, one missing square somewhere. Oh, and by the way, it doesn't really matter, that I started with a missing square here. If I did a missing square here, I could have just taken out those three squares and used my last L-shaped piece there. So suppose you've got a 16 by 16 floor with a missing square, and you ask me to tile it. And I say, sure, give me 20 bucks. I'll give you a tiling solution. All right, so how do I do this? Well, I mentally break this up into 4 8 by 8 rooms. And I have a friend who took this class with me and wasn't quite as greedy, but they advertise they'll tile floors up to 8 by 8 using L-shaped tiles. So I go to this friend and I say, hey, I've got an 8 by 8 room with a missing square. Can you give me a solution? And they give me a solution, and I give them a couple of bucks. And then I go back to them and I say, hey, I've got another 8 by 8 room with a missing square. Looks just like this. Can you give me a tiling solution? And they give me a solution. And I go back to them a third time and I say, here's another 8 by 8 room. Can you give me a solution? They say yes. And then I go back one more time and I say, okay, I got one more room. It's 8 by 8. It's missing one corner. Can you give me a solution? They say yes. I take those four solutions that I got and I use them to tile here, 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 and here. And then I plop down one more tile and I hand that back to you and I say, there's how you do your 16 by 16. But in order to do that, I need a friend who can tell me how to tile an 8 by 8 room. So what does their business look like? I give them a room and I say, hey, I'm trying to tile, an 8 by 8 room with a missing square. And they say, yeah, I can get you a solution for that. And what do? They break it into a bunch of 4 by 4 rooms and they go to another friend who specializes in 4 by 4 rooms. And they say, can you tile this room? Can you tile this room? Can you tile that room? Can you tile that room? They plop down one extra tile here. They hand this back to me and say, okay, here's your solution to the 8 by 8 problem. How does the person whose business is tiling 4 by 4 floors do their job? They're given a room that's 4 by 4. And I can fill this in now. And there's a missing square somewhere. Maybe it's that one. And someone comes to them and says, hey, tell me how to tile this. So they break it mentally into 4 quadrants. And they temporarily X out these pieces. And they go to the person down the street who specializes in 2 by 2 rooms. And they say, hey, I want to tile this room. That's the upper left quadrant. And then they say, hey, I want to tile this room. That's the upper right quadrant. And then they say, I want to tile this room. That's the lower left. And then they say, I want to tile this room. That's the lower right. And they take the 4 solutions they get back. They use it to tile here. They drop down another tile in the middle. And they hand that to me and they say, there's how you solve your 4 by 4 problem. So now the final question, the person who tiles the 2 by 2 floors, how do they do that? Well, you come to them and you say, here's a floor with a missing section. I want to tile that with L-shaped pieces. Can you tell me how to do it? And they say, yeah, and they look on the wall and they've got a chart. And on the wall, they see this picture and they say, oh, okay, take your L-shaped piece and put it like that. There's your solution. And then you come to them and you say, okay, well, I got another problem. I've got a floor with an upper right corner missing. How do I tile that? And they look at their chart and they say, oh, right here, yeah, put your tile down like that. That'll take care of it. They don't need to go to a friend to solve these problems. They've got the solution for all the problems they might encounter hanging on the wall. So after they've figured out for this person how to tile each of these four regions from the chart and they've given the solutions, this person writes the solutions for each of those four quadrants, adds one tile in the middle. They've solved this 4x4 problem. And now this person who's working on the 8x8, they come to this person four times, get those four solutions, pop down one more tile. There's the 8x8 solution. And meanwhile, I'm waiting for my answers. Well, I just got one 8x8 solution. I do that three more times. I get my um, four solutions for the 8x8. I tile each of those regions. I add one more tile here. I've done the 16x16. I give you that answer. You give me my $20 and we're done. So as a business model, I don't recommend this. For one reason, you need to have a friend who does 8x8s, and they need to have a friend who does 4x4s, and they need to have a friend who has the magic solution for the 2x2s. But if you wanted to do this, you don't really need friends. You can do this all yourself. What you would have to do is when you're trying to solve the 16x16, take this and store it somewhere. Put it on your table somewhere and write yourself a bunch of 8x8 problems. This one, this one, this one, this one, and tackle each of those. And once you've solved the first 8x8, right, you've got a solution to that, go ahead and solve this 8x8. And once you've got that and so on. But how do you solve those 8x8s? By solving a bunch of 4x4s. But you can do this all yourself, right? You don't need friends who have the same business model. You can be the one who solves all of these. And you keep handing off work to yourself and you keep changing your hat from, I solve 8x8s to I solve 4x4s and so on until you get down to this base case where you're the person who solves 2x2 problems. And now you don't need to defer that to anyone else. You just take the answer off the wall. And so this is what we're going to do with our computer programs in 222. This is what we started today. It's what we're doing tomorrow. And it's called recursion. And the basic idea is to take a large problem and break it down into a series of smaller problems. And then take the solutions to those smaller problems, put them together. That's your solution to the bigger problem. And to keep doing that. We don't code up a big complex algorithm for solving 8x8s. We break it into the solution of four 4x4s. We get those four solutions, we put them together. There's the 8x8. And to solve the 4x4, we break it into a series of 2x2 problems. But the 2x2 problems, we don't break it down any further. We have hardwired a solution for those cases. So our process of recursion will be very much like our inductive step. And anytime we have recursive functions, we always have some sort of non-recursive solution coded. If n equals 1, then the answer is this. And that's going to correspond to our base case. All right. So to whatever degree that made sense, great. If it made very little sense, that is okay. I wanted to get through this because it's going to be a week till we get back to lecture and because we're doing recursion this week in 222. So this may take time to sort of gel. There's a lot going on here. But give it time, let it come up in your brain as it does, let it be confusing if it's confusing. Run with it if it's starting to make sense, see where it goes. We've got another 5 weeks in this quarter to dig into all of this stuff, and we're going to make good use of that time. But anyway, that's a tie-in between mathematical induction and recursion. We are at 150, so I will call it good here. I will see everybody either in 222 tomorrow if you're in the hybrid, or I'll see you Monday in person for midterms. Have a good rest of the day. and I'll catch you all next time. Thanks.